Jean, do you want to test your slides?
Testing 1, 2.
Yes, please.
In a minute. Does that work?
Yep, looks good.
What do you think, Kaylee? Should we get started?
I was thinking we should probably get started so we can stay close to time. And we got 20 people. I think that's quorum, and we have all the speakers, which is even better.
Okay, sounds good. Well, welcome everybody to our third and final session on SBEO today. Yeah, this one is about some programmatics and missions. And the first speaker in our session is Cassandra Balduk, speaking on behalf of Marcus Stamek and the Canadian Space Agency about our atmospheric science-based missions. So go ahead, Cassandra.
Thanks, Adam. Just share my screen.
Yeah, looks good.
Looks good. Okay, great. So hello, everyone. Thanks for the opportunity to speak today. As Adam said, I'm going to speak on behalf of my supervisor, Marcus Stamek, who cannot be here today. I'm a mission scientist at the Canadian Space Agency in atmospheric sciences. And I'm going to tell you about the Canadian atmospheric science missions and recent results. Change slide. Okay. So we currently have 3 missions to be reporting on. There's Muppet on Terra that has been operating for 23 years. We have Osiris on Odin that has been operating for 21 years, and the SciSat satellite that has been up there for 19 years. 2 years ago, we did a phase E review of SciSat, which led to these results. So in over 17 years of operations, there has been 53 discoveries made by almost 550, and 550 publications using SciSat data, involving more than 1,600 researchers from 350 institutions from 36 countries. This shows the scope and the utility of the SciSat data. And at the time of the phase E review, we identified the most recent discoveries made using SciSat data. The topics are pretty large, and it spans phosgene to Antarctic ozone levels, to production of greenhouse gases, to fire and NO2. And recently, 2 months ago, actually, a new publication was published in Science, showing evidence that wildfire smoke destroys stratospheric ozone when injected in the stratosphere. The second mission we're reporting on is Muppet on Terra, which is currently undergoing a phase E review. The results will be known at the end of the summer. So this is the status of the mission when we last did the review 2 years ago, I think. So now the satellite the instrument is on its 22nd year. It has produced 37 discoveries, more than 480 publications from more than 1,500 authors, from almost 400 institutions in 46 countries. This instrument is an example of longevity, as its mechanisms have performed over 169 billion retrievals. As would Marcus say, this is fantastic. And we've identified the top 5 areas of impact of the Muppet mission. So it's the longest satellite record of global carbon monoxide observations. It provides observation of pollution transport. It helps understanding the chemistry and climate. It helps the prediction of pollution and air quality using data assimilation. Sorry. And it provides unique height resolve tropospheric carbon monoxide retrievals. Last summer, we've conducted our most recent mission review of Osiris, and it celebrated its 20th anniversary last February. So it has produced 32 discoveries, 265 publications from more than 860 authors in 230 institutions from 26 countries. And it has measured over 3.2 million atmospheric profile scans. This alluvial plot shows the entirety of the publications that were produced using Osiris data across its 22-year existence, categorized into 4 broad categories, which are shown on the right. So these categories are the measurement and profiles of gases and aerosols, comparison of Osiris data to other measurements, usage of Osiris data in numerical models, and the analysis of clouds and volcanic activity. So for each year, we show the number of publications in each category. And we see that each category waxes and wanes, but none of them disappears or takes over. So they all remain pretty relevant over time. The most recent discoveries made using Osiris data are shown on this slide. It includes an article in Nature about the 2019-20 Australian wildfires, another article about the solar cycle response of ozone, and a paper here published in Nature describing the detection of ozone recovery, as well as volcanic aerosols and stratospheric circulation, and many others. This slide shows the data collaboration over time. So it basically shows the number of author per publication plotted on the time axis to see how many authors collaborate together over time. And it shows that there's a large number of researchers collaborating, actually using data sets including Osiris. It illustrates the broad interest of the community and the continuing impact of the satellite for atmospheric and climate studies. And in the purple circles, we have the number of authors, and in the green circles, we have the number of countries involved. We wanted to show you some data from particularly Osiris profiles. This plot on the left shows ozone profiles over Antarctica, and we can clearly see the ozone hole during springtime in Antarctica. And this shows a 50% decrease of ozone concentration compared to the 20-year average. Another well-known Osiris data project is the Aerosol Measurements. So this is a summary of the last 20 years of Osiris ozone data. It basically has measured every volcanic eruption that has made it high enough in the atmosphere for the instrument to detect it, as we can see on this time series below. And this shows the worldwide distribution of data users. All of our missions have an extensive list of data users, such as this one, and it shows that the typical users for Osiris data are, well, Canadian institutions, institutions from the US, obviously, and Europe. and a couple of players in Asia. This shows an extensive list of space-based instruments that have been compared or calibrated or validated using Osiris data. There are in total 33 instruments on 23 satellites, including a few Canadian instruments. And over the years, Osiris data has been merged with many different other data sets to produce combined data sets, combined climatologies and long-term data sets. And the two main types of data sets are ozone and aerosols data sets. And the most recent ones are here on the right. So there's the SAGE-CCI OMPS ozone data sets, the global space-based stratospheric aerosol climatology, GLOSAC, and the merged gridded data set of ozone profiles, MEGRIDUP. This slide shows all the numerical models that are used to advance Osiris data. There's 36 of them, and we've classified them into 4 broad categories: the radiative transfer models, chemical transport models, climate or general circulation models, or specialized models. And they can be found in 91 publications. And last December, the government of Canada conducted a workshop to present methane science and technology. I won't go into the details here, but we've conducted an analysis of how SciSat and Muppet data advance methane science over their entire mission duration. So when we analyze all the publications using those data sets, we identified 12 discoveries related to methane, more than 100 publications using these satellites to advance methane science by more than 600 researchers in 170 institutions in 27 countries. And we wanted to show us an example of data. Here we have more than 17 years of methane profile from ACFTS on SciSat. On the left, we have here for the whole atmosphere, we have a zoom between 5 and 19 kilometers here in the center. And on the right, we have this time series that shows the slow increase of methane over the last 17 years. We identified five areas of study advancing methane. So these include the publications analyzing methane emissions and distribution over space and time, so the transport, publications doing the data retrieval and scientific comparison. So basically analyzing instruments, their data retrieval algorithms, and so on. The third category is the publications treating methane as a precursor or tracer for other gases. So here methane is generally not the main concern. Another category has analyzed the methane impact on climate change. And finally, a few publications discuss methane detection on celestial bodies. Oh, and that's it for me. I'm ready to take questions if we have some time. Yep.
Okay, thank you, Cassandra. Very nice.
Thank you.
Questions? You can put your question in the chat, or you can put up your hand or just turn on your mic. Feel free. Okay, all right. Thank you, Cassandra. Maybe we'll move on. Thank you.
Thank you.
Okay, next we have Hiba. You can go ahead and share your screen now.
Sure.
And Hiba will tell us today about Muppet and Yazi. Go ahead.
Yeah, sure. Let me put it in presentation mode. Everyone can see it.
Yeah, looks good.
Excellent, thank you. My name is Hiba. I'm working at University of Toronto with Jim Drummond from Muppet. And today I'm gonna show you some results of Muppet and ESE satellite comparison. And this is a joint project between University of Toronto and MCAR in Boulder, Colorado. And the main outlines that's going to be in the talk today is to present some daily data column of ESE and Muppet averaged over the domain of North America and the spatial variations of both of them, plus comparison of some selected days based on the availability with the corresponding collectible files, and also to compare them to TCON and NDAC data sets as well. So as Cassandra mentioned already, that Muppet is an estimate that measures atmospheric carbon dioxide since 2000. And the unique thing with Muppet is it does have actually two channels to detect carbon dioxide, one at TIR and the other one at NIR. So the joint product of both of them actually gives better sensitivity to measure carbon dioxide near the surface. And the main characteristic or the main differences in the characteristic of Muppet and ESE, first of all, in terms of retrieval, Muppet is using correlation radiometry, as I just mentioned, TIR and NIR, while ESE has a wider spectral range from 3.6 to 15.5 micrometer. And the temporal resolution of Muppet is about 3 days, while ESE has a daily temporal resolution, and this is because the swath width of ESE exceeds the 2,000 kilometer, while the swath width of Muppet is about 640 kilometer, with a pixel size of 22 by 22 kilometer, while the horizontal resolution of ESE is about 12 kilometer at meter. So the other thing as well is the main difference between both of them is Muppet is using a variable a priori profile in retrieval, variable in terms of time and location, while ESE is using a fixed a priori one. And for some retrieval parameters, such as emissivity, Muppet is retrieving them, while ESE is assuming a fixed one. And in terms of water vapor, ESE is estimating them, but Muppet is using a fixed ones from NSIP data sets. So as a motivation of the study, you can see here in the last, especially 20 years, that there has been actually an increase in fire activities, especially in the area of North America and the Western, exactly the Western parts. And as you can see here, the highest peak was shown in 2020, which relates to the huge fire activity that occurred in September in California. And that's why we choose actually that time and that domain for the analysis. So we'll be focusing more in August, September time, and for the North America domain for the sake of the analysis and comparison. Okay, so you can see here for the left-hand side, this actually shows the carbon monoxide total column averaged over the domain that we just saw, the North America domain, and those actually the collocated ones between Muppet and ESE, because there is a difference between the temporal resolution between them. So just actually for the comparison, we selected the collocation ones. And as you can see, sometimes they are going very well, very consistent. And this actually when the CO emissions are typical, but when there is an actually high CO disturbance, ESE sometimes is higher than the corresponding Muppet. And I forgot to mention that this actually for August 2020, where we are focusing in August and September for the times of the high CO emissions from the fires. The right actually plot is showing the corresponding profiles, CO profiles for both of them averaged over the same domain. And as we can see, those actually high ESE total column might be reflected as a reflection of the high CO from the near surface to about 500 or 600 of ESE relative to Muppet. Having the same plots for September one, we can see on the first 2 weeks of September how actually both of them are going very well consistently. And again, because this is the time of typical emission before actually the huge fires coming here. And then through the second week and third week, we can see about 20% of discrepancies of EAZ relative to the corresponding Muppet. Looking to the corresponding collocated profiles, we can see here that EAZ is showing higher CO near the surface again, and it becomes close to Muppet when we go higher to about 500 or 600. So going to the, so before I go to the profiles, we thought then if those actually discrepancies happens when there is a high CO emissions, we thought if we actually filter those high actually CO values above 3 times 10 to the power of 18 molecules per centimeter square, let's see how both of them will be behaving. And as you can see, filtering those high data shows that how both of them are quite actually consistent together. And it's the same actually for the profiles, where the profiles of EAZ become actually more close to the corresponding Muppet ones, again averaged over the same area for September. So looking to details profiles day by day for the same month, we can see actually how both of them actually were able to detect the pattern of the signal emissions from the fires in the second and third week kind of that month. However, the Muppet actually values didn't exceed 250 ppb, while EAZ ones, sometimes they were exceeding even 500 ppb for some days. Where are actually mainly those actually happening? Looking to the special variations of the carbon monoxide total column for September. And again, both of those are just the collocated ones between both of them. So we can see in some regions, actually, some regions, there are some discrepancies between them. For example, here over Hudson, we can see here the total column is much higher than the corresponding Muppet. The same over Quebec or in this area, Southern Ontario, or Northern US. And this is actually reflected in the correlation coefficient between them, which is 84%. And the slope is 1.2, giving an impression of 20% EAZ values higher than Muppet. And this is because the discrepancies for some regions that we just highlighted right now. So going more close in some selected days and to compare actually those to the available Calypso data. For example, this September 2020. And again, those actually the EAZ ones that just match or collocate the corresponding Muppet ones, because as you know, EAZ still has wider actually swath, which gives it more data, but we just selected the collocated ones to make it fair comparison. And as you can see here over Hudson Bay, how actually there is really significant discrepancies between the values of EAZ relative to the Muppet ones. It's about even the bubble one, which is reflected in the profiles again, where it's higher than Muppet from again near surface to about 500 or 600. And the same here for this area, the Southern Ontario is still higher, which is actually in terms of profiles, as you can see here, Muppet didn't exceed even 250 ppb, while actually EAZ ones is more close to 400. So then we thought if there is actually a high CO emission near surface, we might actually have high intense load, aerosol load near surface. So then it does what might be to look to the available Calypso ones, although it does not actually match the exact time. So this is, for example, nighttime, this is daytime, but it might be a proxy of what's happening. And you can see here in the Calypso for those actually two regions that the intense actually emissions are happening, or the aerosol emissions are happening in the middle troposphere and in the higher troposphere, and we couldn't actually find something near to the surface as it's shown here by EAZ. Looking to another day as an example again, the next day, 21 September 22. And as you can see here again, there are some discrepancies over Quebec of EAZ relative to the corresponding Muppet one on the right-hand side. And the same here over Saskatchewan. Also, Muppet is showing higher values as well relative to Muppet, which is again very reflected in the profiles. The average profile for that area for EAZ are going to 500 ppb, where Muppet didn't exceed 200. So again, we were curious to see if really, again, Calypso can actually detect any of those high values near the surface and still the emissions are shown in the middle troposphere or even the higher troposphere. And again, this is nighttime and this is daytime, but just something, it's not easy to find Calypso at the same time exactly and the same location. So then we thought it might actually then worth it to compare both data sets to be available in EDAC and TCON. And then we choose actually 4 stations in the domain. The criteria for the collocation is about 1 degree. So where actually we centered the equation for the station in Muppet and EASI plus or minus 0.5 degree, which is about 1 degree. And the time frame is for those stations is 4-hour morning to match the daily Muppet and EASI ones. So since the criteria selection is very tight, it's not easy to get a coincidence between all instruments. However, we can see when there is a typical emissions, all the instruments are going well. However, again, when there is a high disturbance, CO disturbance or high emissions, although there are few data, but we still can see actually that EASI, which is the blue one here, represents EASI and the red one represents TCON. We can see, for example, here how EASI is 20 to 30% higher than the corresponding TCON. Here, there is a little bit actually higher values. The same over Lomont here, where we can see there is a very significant differences between this blue one, which is EASI, and the red one, which is TCON, and the same here over Edward. But again, because the selection criteria is very tight, we don't have like too much data, but we can still see some of those disturbances at the time of the extreme high CO emission disturbance. But when there is a typical emission, again, they are all going quite well together. So looking to the NDAC, the available one, which we choose actually Toronto Station, it's the same selection criteria, 1 degree and 4 hour in the morning. And we can see here in the second week of September, how the blue ones, which is EASI here, are significantly higher the corresponding Muppet one. Looking then in the profile, because as you know, in DAC they have profiles, so then we thought it was worth it to average the Muppet and EASI profiles over the same area. And we can see here that EASI sometimes are showing values that exceed 400 and 500 again, which is not shown at all in the corresponding NDAC. The available Muppet, again, because of the criteria is very tight, the available Muppet data are not that too much as EASI. However, it's more close to the NDAC, the available NDAC and the corresponding NDAC than EASI. So then trying to understand what's happening, and as we mentioned, the main difference between both of them is the choice of the a priori, where Muppet is using a priori that's variable in terms of time and location. However, EASI is using a fixed one, and this actually reflected in the equivariance matrix of both of them. So we see here the right-hand side, the covariance matrix of EASI, how the off-diagonal elements of EASI are more variable than the corresponding Muppet. And the off-diagonal elements of the covariance represent the correlation between different layers. So we can see here how this correlation is about 63% near the surface, and then it's going to go to about 30% or 35%, which is similar to the Muppet one. And again, in the higher troposphere is going to exceed 45%. And this actually might explain those differences in sensitivity near troposphere, as we just saw in the profiles, where the correlation length of EASI is different than the corresponding Muppet, and it's more variable than Muppet. So then, in
1 minute, Heba?
Sure.
Oh, great.
Yeah, I'm good in time. I have 1 minute, you said? Sorry. Okay. So in conclusion, we can actually say that both Muppet and EASI, when there is a typical CO emission, they are going quite well consistent together. And we actually did, in this talk, I focused on August and September, but when we did this for the whole year, actually, most of the year when there is a typical emission, they are going very well consistently together. But at the time of extreme CO emissions, we can say that EASI is higher than Muppet, and this is because of the high CO values in the lower troposphere. And this is actually because of main factors, but as we saw that the main factor between them is the difference in vertical sensitivity that's results of the difference in covariance matrix, and this actually reflects in both sensitivities to the lower tropospheric emissions at the time of the extreme CO disturbance or high fire or the fire emissions. And in the meanwhile, we're trying actually to add more data set for the comparison, because as you can see that in the Corticon, we have few observations to compare. So in the meantime, we're comparing both of them to the available TROP-OMI, and it's still in progress. And that's it, and thank you.
Great, thank you very much. That was good. Questions? That's good. Well, I very much like the comparisons to the ground-based sites. Wondering what you think the next steps are beyond that. It looked kind of good, but also there are some questions about the agreement levels.
Yeah. It's not easy. It's tricky. That's why in the next step we're trying to do two things. Number one, as I mentioned, trying to see the TROP-OMI to compare the total column TROP-OMI to both of them. Number two, since we concluded that when there is actually a high CO disturbance, both of them, they don't agree too much, then we are thinking right now to select other areas other than actually this Canadian or North American regions, select other regions that also experience the same fire activity, and then we're going to compare AZ and Muppet there and to see how they behave, if the behavior is the same or not, in order to have a general conclusion of that behavior, and also to see if there are more in situ measures there to use it as well. But we're curious right now to see if this behavior actually is general. So we're trying right now to see similar regions for the comparison, and to get more global data, I'm trying to use TROP-OMI as well. Yeah.
Okay, thank you.
Thanks.
Oh, a question from Aldona.
Hi, Heba, can you hear me?
Yeah, sure.
Thank you for a nice talk. Have you showed the a priori covariance matrices? Have you considered the averaging kernels of IASI?
Yeah.
And whether or not the sensitivity of IASI is vastly different from Muppet for some reason near the surface?
Yeah, it's a good question. I didn't show the result here because it was not conclusive and it didn't resolve the problem. I did smooth both of them using the averaging kernel and then do the comparison, and it did not help at all. And I think there is an article to Maya that was published in 2015, and she did something also using the smoothing averaging kernel of Muppet using IASI to see if this will resolve the problem. And also she got the same results, that in some regions it was better, in some regions even it was worse. So it didn't actually help. That's why I haven't included it. But yeah, I did look at it, and it's it didn't actually improve the discrepancies or help to reduce it.
Okay, good. Thank you. Let's move on to the next talk then. Doug, you can take control.
Let's see if I can. How am I doing?
Yep, looks good. You can try it in full screen.
I just tried it and tried again, and it looks like it worked this time.
Yeah, it's good. All right, so Doug Degenstein, Osiris on Odin.
Okay, everybody. This is the third time I've given a CMOS talk from Saskatoon. Conference is actually in Saskatoon this year, so that's good. You'll note that it now says my office instead of my basement, which it said in the title slide for the last couple of years. Osiris on Odin, 21 years and counting. And the list of people down at the bottom are the people who actually contributed directly to this talk, but there are many, many, many others. And I'd like to thank Cassandra for doing a very good job of introducing all of the things that Osiris has managed to do over the last quite a few years. And I'd like to really thank the team that's been part of it. And I guess thanks to Kaylee and Adam for organizing this as well. I'm going to keep my stuff brief today. I'm going to do a little introduction, and then I'm going to talk about some recent activities. And these were led by Christoph Wagner, Kimberly Dubé, and Landon Rieger and Taryn Warnock. But once again, there are lots of other people who contributed to these. These activities are related to the ozone, NO2, and the stratospheric aerosol, which are the prime products from Osiris. So what would an Osiris talk be without a picture of the rocket that launched Osiris in February of 2001? So that's why it's 21 years and counting. We are now, from the moment we went up, and we are still operational, we have now lasted longer than Sage 2, and I'll talk about that in a little bit. We don't know if we have a longer data record yet. We have to check into that. But Osiris is an optical spectrograph. It's a single line of sight, narrow slit, grading spectrograph that measures from 280 to 810 nanometers with about 1 nanometer resolution. There's another channel, the infrared imager channels, which I'm not going to talk about much, and these measure mesospheric emissions. But the spectra you see in the upper right-hand corner here, these are your typical Osiris data products, wavelength and radiance, and those are for different tangent altitudes. So I have given this talk in a number of different places, and the LIM workshop last year, I think I put this slide in, and I'm going to leave it in, but I'm not going to dwell on it. But basically 21 years ago, for a handful of small handful of millions of dollars, a dedicated team built a spacecraft and an instrument, and it's been in operation for 21 years. And the knock-on effects are still being felt all over the place. We've got the Sastran radiative transfer model. We've got the SHOW and ALE instruments, which were mentioned earlier on today. We're using our technology to help the European Altius mission and plenty of other good science. And I am incredibly proud of the team of people over the last 20 some years who have been involved in this. But eventually it's going to come to an end, but not quite yet. Right now, in 2022, our orbit is somewhere in between 500 and 550 kilometers. And the projection here is it's going down. We are closing in on the Sage 2 LIM observation record. We've got a few good years left in us. Probably 5 for sure. There's no reason why we can't last 5 more years, but at some point in time, we will start to come down fairly rapidly. So I won't be able to give the update talk probably 7 years from now. Our data collection duty cycle has dropped a little bit as we age, but in 2021, we collected over 10,000 scans, and a scan is a set of LIM measurement spectra that are used to retrieve ozone, NO2, or aerosols. These scans have been distributed over more than 250 days of the year. And what these two pictures here show is that 2022 is just as good as 2021, which was maybe even slightly better than 2020. So as far as our data collection goes, number of calendar days with measurements and number of scans. We measure LIM scattered sunlight. So we look from the Odin spacecraft along the line of sight, and we measure scattered light coming into the instrument, scattered off the molecules and the aerosols in the Earth's atmosphere. And to simulate that, and no Osiris talk would be complete without a plug for the Sastran radiative transfer model. To simulate these measurements, we use in-house developed code that has been, I'd say, almost perfected, but still getting better. We've been developing it for over 20 years now, 25 years. And there is a website, arg.usas.ca. We'll get you partway there and look for the Sastran. Anybody who wants to use the Sastran radiative transfer model, we are more than happy to help you get started. Easy to use Python code. The Osiris data products. So I've mentioned these a couple of times. We measure ozone, stratospheric aerosol, stratospheric NO2, and stratospheric BRO. And you'll note here for the first time, we've got version 7.2 of all of the species except for the BRO. They have been number density and drift corrected. The ozone has an improved cross-section and spectral point spread function. The stratospheric aerosol has an improved cloud detection, and I'll talk a little bit about each of these later on. The stratospheric NO2 was improved to correct for a low bias in NO2. These data products are incremental improvements, but still significant, and they have just recently been released, the version 7.2. All products now are processed simultaneously and updated monthly, which is nice. We're starting to get to the point after 21 years where we can produce our data on a regular basis. Version 7.2 resulted in a lot more profiles for each of the species, except for ozone, which we'd concentrated on primarily in the past. But we've now got 43% more aerosol profiles and 37% more NO2 profiles. And we are pushing these further and further down into the UTLS, and you'll see a little bit about that later on. So recent activities. So a little bit, we talked about the data products. Now, what are we doing with those data products? And ozone recovery is one of the main things that we do. We're a key contributor to long-term to studies in the long-term change in the ozone profile. These studies are being done by groups like the Lotus Group, which is commissioned by SPARC, which feeds into the WMO ozone assessment. And every year we update the bulletin of the American Meteorological Society State of the Climate. And I borrowed this figure, and you can clearly see here at the higher altitudes, the 2 hectopascal altitudes, 42 kilometers, all of the data sets show ozone was going down, and now it's going back up. But at 50 hectopascals or 22 kilometers, there's a slightly different story. And still to be determined, and lots of good work to study as far as the change in the ozone profile with respect to time. The previous slides highlighted two SAGE-2 and SAGE-2 Osiris-based data records, one with just SAGE-2 and Osiris, and the other was SAGE-2 Osiris and the OMPS LP University of Saskatchewan 2D product. We recently, and this was Christoph's work for the most part, completed work on merging the SAGE-3 ISS data with the SAGE-2 Osiris data record to make an SOS data product, SAGE-2 Osiris, SAGE-3 ISS. This work was done mainly by Christoph, will be taken over by Kimberly, and is supervised by Suzanne. And Christoph did the work that's going to be highlighted in the next few slides that talk about ozone trends. So he did a comprehensive study or comparison between version 7.2 and version 5.1. And this work that I'm going to talk about here has been submitted to ACP. It's in the discussion phase right now. And we looked at drifts between the two data products, the two Osiris data products, and the monthly zonal mean differences. And the things that we tried to fix, basically this picture says we did a good job of fixing them. Drifts and certain things that showed up at different times of the year. Now to look at trends. So these are the typical trend pictures. We have our predictors. We fit El Nino. We fit two principal components of the QBO. We fit the solar cycle. We fit aerosol. And we do a multivariate linear regression trend analysis and a dynamic linear model trend analysis. They both basically show the same result. Ozone in the stratosphere above, let's say 33 kilometers, is increasing at all latitudes, but the picture is somewhat different below that altitude, and it gets even more mixed up as you get close to the tropopause. The DLM has an advantage. The dynamic linear model doesn't just fit straight lines to the trends. It actually looks for changes in the slope of the trend line at any given time. And these pictures here highlight, as a function of time, the change in ozone at any given time at different latitudes. So here, this is -60, this is +60. These are altitudes, and you can see that in this one here, for instance, -50, ozone decreasing up until about 2004 and then increasing. That's not the case at all latitudes. Ozone decreasing, ozone increasing, and then ozone is decreasing again at 60 degrees and 50 degrees. So in the northern hemisphere, which is slightly different than the southern hemisphere. So we have done a little bit of work comparing these trend results to models. The CMAM model, and David Plummer has provided us with a lot of good CMAM data, and Christoph has now moved on to something else, and Kimberly Dubé will start to take over this work. So this is fairly preliminary, but what you can see here is that the CMAM model trends and the trends from the SAGE Osiris SAGE data record show similarities. And they also show an asymmetry in their hemispheric response. So at low altitudes, just above the tropopause, lower stratosphere, decrease in ozone in the northern hemisphere, but not in the southern hemisphere. And that's seen in a few, but not all of the realizations of the CMAP model. So this work will be ongoing, and Kimberly Dubé will be doing it as part of one of the CSA Earth System Science Data Analysis grants.
1 minute, Doug.
Sorry, 1 minute? 1 minute? Okay, I'm almost done then.
Good.
The NO2, Kimberly has also been working on NO2, and this picture here shows that we have fixed the low bias in the NO2. This picture here says we agree quite well with ACE and the SAGE 3 ISS NO2. And this picture here is the good one. It shows that in the Asian monsoon, daytime NO2 is lower within the UTLS of the Asian summer monsoon, whereas NOx is elevated in the same region. And that information is pulled out very nicely in these bottom two slides or pictures here using Osiris data and the Pratmo model. And aerosols. We talked about aerosols a little bit this morning with the ALI instrument, which is a follow-on to Osiris. Aerosols, we've been measuring volcanoes and stratospheric aerosol optical depth for 20 years. We have a very good 20-year record, which is at the top. We can take that record and we can look at the Osiris and SAGE 3 ISS measurements at the same time for 2018. And we have Australian fires, we have Rayakoki, we have the La Soufriere volcano, we have Hungatanga. Hungatanga is complicated. All the instruments that are measuring aerosols for Hungatanga are seeing different type things. I'll leave it at that. And Osiris measurements continue to come in, and every year new science continues to come out. So thank you.
Good. Thank you, Doug. We can maybe do one quick question. Going once, going twice.
Your question.
Okay. All right. Let's leave it at that. Kaylee, I think we're supposed to have a quick break here, right?
Yep. So I think we've got 5 minutes.
Sure. Okay. See you all at 10 minutes to the hour.
Whatever your time zone.
Yeah.
Don't forget Newfoundland.
Right.
I'm
Sorry.
blaming the jet lag.
Are you ready to start?
Let's go with I was ready a while ago.
Believe it.
Okay, how does the visual look?
Yeah, looks good. Okay, so for the last part of our last session today, our first speaker, Dr. Kaylee Walker from the University of Toronto.
Okay, thanks, Adam. So I'm going to talk about the youngest of the 3 satellites that Cassandra introduced to us earlier in the session. I'm going to talk about some validation and science results from the Canadian Atmospheric Chemistry Experiment. This is a fairly slanted view of it because there's so much that's been done. I'm presenting what came from my group and some of our collaborations with Environment and Climate Change Canada. So just to remind those who might not have been paying attention a little while ago, but ASON SciSat is one of the small sats. So it's a meter in diameter and a meter tall. And we focus on profiling measurements of trace gas species, clouds and aerosols, and temperature and pressure. And we started out at the time when we were designed to really be focused on ozone, but over our lifetime, we have really grown into looking at the effects of biomass burning, looking at chemistry climate coupling, and all sorts of really exciting things that you can do with a solar occultation satellite. We're also in a fairly highly inclined circular orbit, which you will hear how that impacts what we do. So as I said, we do solar occultation. So we stare at the sun and then make measurements as the sun either rises or sets as seen from the satellite. And we have 2 instruments that are doing that. The Fourier transform spectrometer working in the mid-infrared, which also has 2 half and 1 micron imagers with it, and the ACE Maestro, which was added in the development of the mission to provide a UV visible and near infrared component. Our time series starts in February of 2004 and is still going on today. Because we do this solar occultation technique, we have to have the Earth, the satellite, and the sun in the right configuration, so we can make up to 30 sunrise and sunset measurements each day. Much like Osiris and Muppet, we were designed for a short mission lifetime, and we're now in our 19th year in orbit. We're starting to see some degradation in the FTS performance, but that's a small decrease in our signal to noise ratio and nothing that's had any significant impact on our retrievals. And the ACE Maestro lost much of its UV measurement capability early on in the mission, and it continues to age gracefully. Now you may ask yourself, well, why would you bother to do measurements when you can only do 30 of them per day? And this lovely eye chart is the reason why we like to do these measurements. The wealth of information that you can retrieve from a solar occultation spectrum, particularly in the infrared, is massive. So the things that we have highlighted here in red are those specific species and parameters that we promised to the Canadian Space Agency in the initial proposal and for launch. Everything else has been added on, and the latest version 4.1, 4.2, is the new things we added are shown in blue. We're about to launch version 5 sometime in the next couple of months, and we're adding several more molecules. So we continue to be able to mine this wonderful data set that we've collected. The Maestro provides us with higher vertical resolution measurements. So that's complementary to what we get from the ACE FTS, and we get nice imager profiles of extinction and aerosol extinction. So what I'm going to do is focus on chlorine-containing species in the validation part, and I've decided to pick water vapor as the thing for the theme in the science. So let's move into that. So the first thing I'm presenting on is some of the source gases. Chlorofluorocarbons were some of the initial species banned by the Montreal Protocol, which was basically about 10 years before we were proposed. And so this is an important thing in terms of thinking about where we came from. And we're one of the few things that has this time series. So I'm presenting work by Ali Jalali, who was doing comparisons between the MIPAS instrument, which was on the ESA satellite Edisat, and they have a new retrieval version for their approximately 10 years of data. We're comparing to the part that well overlaps with ACE FTS, and looking at how well these two match enable us to look at how we can merge the data sets. So the things that we're showing here, hope you can see. On the left-hand side is the average profiles from MIPAS in red and ACE-FTS in blue. Then we have the differences, the relative difference, both as the mean relative difference and the relative difference from the mean, and then the correlation coefficients. And you'll notice there's this little jog at the top, and this is because different profiles have different highest altitudes depending on latitude. And so because we have more of the CFCs at the lower latitudes, and those go to higher altitude, it just means that when we make this global average, we've got this little jog. It doesn't impact our differences. Typically, for these latest versions of ACE-FTS and MIPAS, our differences are less than 10 parts per trillion and within 10%. And this is definitely an improvement on the last versions we had, where we were within 10 to 20%, and MIPAS was higher than ACE-FTS. Now, the CFCs, when they were banned, were replaced by hydrochlorofluorocarbons. And the main one that was the replacement is HFC-22. And this is work that Felicia Colangeri started and has been taken over and continued by Patrick Schiess, looking at the validation of this product. So doing comparisons with MIPAS, doing comparisons with balloon-borne instruments and with the Carabic aircraft measurements, but also looking at the trends in these, particularly because the HCFC has also been banned under the Montreal Protocol, and so it had a very strong increase, but we should be starting to see the level off. And what we're looking at here are the two lowest, or the lowest levels. So we have surface measurements from the NOAA surface flask measurement network, and then we also have the lowest altitude from ACE-FTS of 5.5 kilometers. And both of these are compared with sampled or subsampled simulations from the Canadian Middle Atmosphere model that Doug just mentioned. And you can see very good agreement between the two of them. So that shows us a nice correlation between the surface measurements and the 5.5 kilometer measurements. So these were fits done using multiple linear regression with a breakpoint analysis. So in all cases, we end up with a breakpoint somewhere in 2012. And if we compare the pre-breakpoint shown in red and the post-breakpoint shown in blue, you can see a very statistically significant increase in that trend. From the red to the blue, a very good agreement across the different data sets and simulations we're using. When you use the entire HATS surface record, which goes back to 1996, you can see the impact in the pre-breakpoint of that slow or that buildup of HCFC 22, so that that trend isn't going to be exactly the same as it was from 2004 to 2012. So in addition to looking at our source gases, we also look at the active chlorine, which is involved in destruction of ozone. This is chlorine monoxide, which is a very critical molecule. And these are comparisons for the new CLO that was retrieved in our version 4 from ACE-FTS. So this is comparing to MIPAS, to Aura MLS, and to the SMILES instrument, which was on the International Space Station. A diurnal variation in CLO, which means that we need to account for that. We do that using a chemical box model to scale our comparison profiles to the local solar time of ACE. Now, the comparisons shown here vary in the time period. The SMILES are about 6 months maximum. And because of the way that SMILES was mounted on the ISS, it was tending to point towards the northern hemisphere, so we didn't get southern hemisphere polar vortex measurements. The MLS, on the other hand, is essentially the same length as ACE-FTS. And if we look in the northern hemisphere, shown on the left, in the southern hemisphere, both of these in the polar vortex, shown on the right, our differences tend to be within plus minus 10 to 20% in the northern hemisphere, and shifted to a little higher bias in the southern polar vortex. So this is also really neat for being able to try and tie together our measurements where we've got all the different species of chlorine and understanding how well we measure each one of them so we can look at that consistent picture. And this is work that was started by Niall Ryan and is now being completed by Laura Saunders. So moving on to the science side, there's been some really cool things where we look at different events. And Cassandra mentioned in her paper, this really neat science paper that came out of Peter Bernath's group. Another example of one of these experiments in the atmosphere, which happen naturally, is the Hungatanga, excuse me, Hungatanga Hunga Hapai eruption, which Doug mentioned as being complicated. Well, for those of you who remember something happened in Tonga, this was an explosive eruption from a submarine volcano in the middle of January this year. So there's the latitude and longitude, and these images here are actually stereoscopic images that were put together from two geostationary satellites, which were looking at slightly different angles. And this is every 10 minutes, you can see the evolution of this eruption. It was huge. There were ionospheric disturbances. There were tsunami alerts. The plume ended up touching up into the mesosphere. It collapsed fairly quickly down into the stratosphere, and the impacts were mainly in the stratosphere, as we'll see on the next page. So this is analysis that Patrick Schiess has been undertaking, looking at the period where we made measurements immediately after the eruption. And so what that looks like in terms of our measurements is that we don't make measurements at the same latitudes all the time. So this is the pattern of measurements in the bottom on the right over 1 year. And this box shows that period in 2022 between plus 10 degrees and minus 30 degrees. And you can see this is water vapor at 24.5 kilometers, and you can see a strong enhancement compared to the other times of year. So Patrick's comparison shown here in the profile plots at the top. The climatology is all years from 2004 to 2021, and the red profiles are the ones that we have for 2022. And you can see in the aerosol extinction from our near infrared imager, which is very similar to what we see for the visible, and this similar enhancement in water vapor at about the same altitude. And we also see a strong enhancement in SO2 is really kind of interesting. And what's happened here is that we've had a strong injection of water vapor into the stratosphere, which is about equal to about 10% of the total water vapor in the stratosphere. So right now, Patrick is working with our colleague Dave Plummer to try and think about how we could model the impact of this. So
1 minute,
stay
Kaylee.
tuned. Yep. So the last one I'm going to show is the mesosphere, because sometimes you've got to show things that are well above the fundopause. And this is work by Paul Jeffrey, who looked at doing multiple linear regression and fitting a number of different components here. And he was fitting every kilometer from 40 to 90 kilometers. Interesting things happen. Which is basically very positive in the mesosphere. And the connection to these solar cycle is positive over most of the latitude regions that he was using in this analysis. And this is a positive response that's also been seen below 70 kilometers in studies by Aura MLS, Halo, and Sabre. But exactly what's causing it, we don't seem to see the same things that they were using as the explanation. And so with that, I'm going to thank you for coming to see my talk. I hope I've convinced you that we've moved from being an ozone focused mission to a climate focused mission. We've got lots of species. We have lots of data that's available if you're interested. You just need to register. If you'd like data quality information, that's also available. If you like climatologies, come talk to me. We are funded by the Canadian Space Agency, and this work was also funded by the Natural Sciences and Engineering Research Council of Canada. I thank the Science Operations Center at the University of Waterloo, our mission scientist, Peter Bernath, and project scientist, Chris Boone, as well as our colleagues on the MEPAS, MLS, and SMILES teams, as well as Karabic, HATS, and Mark IV teams, and you for your attention. Thank you.
Great. Thank you, Kaylee. Nice talk. questions for Kaylee?
I have a question. This is Hind.
Hey,
Sure.
Hind.
Hi, Hind. Go
Yeah,
ahead.
I can't see yet to raise my hand. Yes. Nice talk, Kaylee. I really wanted to attend your talk to know more about the work you're doing. I was really intrigued by this eruption and the 2022 data, how it differs from the rest of the previous years. If you can go back to that slide. Yeah, this slide here. So this is the whole year, like from January to December for 2022. You're showing.
No. This is just February 2022.
Oh,
So
this is February. Okay.
This box here,
Yeah.
that's all of 2022 we have in that latitude range for the average.
Okay. So and then
And everything else is averaged all over the years.
Right. Yeah. So if you remember when in the 90s when we had the volcano eruption in the Philippines and that caused global cooling that lasted 2 years, people use that an example for the effect of sulfate injection into the stratosphere, I believe. Yeah. So was there any temperature results from this analysis or?
We're looking at lots of different correlations. The signal, my feeling is that we were able to see what came from Mount Pinatubo by being able to look a number of years afterwards. Like you need the data set afterwards to be able to see the effect. And so that's why at this point, we're looking at modelizing to see if we can predict what the effect is. And this is also kind of interesting because Pinatubo didn't throw that much water up. So this not only has sulfate aerosol, it also has water vapor,
Right.
which I think maybe some of the reason for Doug's description of no one's seeing the same thing. And it might be because we're looking at different times and chemistry has happened. As you and I know, chemistry can always be fun.
Right. Okay. That's really cool. So, and you mentioned in the beginning of your talk that the satellites itself, you're starting to see some signs of degradation. Do you think you will be able to collect years after this event to be able to analyze back how things compare to 2022?
The maximum signal to noise ratio we had on the FTS was 475 and the requirement is 100. We're seeing decreases into the lower 400s right now. We got a while to go.
Okay, that's good. Well, that's exciting. Thank you.
Thanks, Hind.
Great. Okay, thanks, Kaylee. We should move on. Okay, our next speaker is actually back to Cassandra again. Cassandra is going to tell us about the results of the CSA's Data Analysis Grants Program.
Yes, can you hear me and see my screen?
Yep, sounds fine. Thank you.
Okay, thank you. Okay, so here I am again. Yeah, as Adam said, I'm going to present the preliminary results from the analysis of the PI surveys from the data analysis grants in atmospheric sciences. This is pretty fun because I know many of our grantees are in the room today, so I hope I'm going to see some nice results for you. Okay, so the AO for these grants was published in 2016, and the funding started on April 1st, 2017. There are 12 grants that were awarded. 7 of them are now complete, and 5 of them have been extended for 1 more year. So that makes 6-year grants, and some others have been going on for 4 or 5 years. The main objectives of this AO was to advance the understanding of physical and chemical processes in the atmosphere and to develop or improve numerical models. And to be eligible, the projects must use data acquired by Canadian satellites, instruments, or subsystems in space, or complementary data. So this slide shows a quick summary for the 12 grants that cover, broad range of topics. And this slide shows the distribution of projects across Canada. So as I said, 12 proposals were funded and 35 researchers are involved. 29 are from Canada and 3 are from the US. They involve five institutions from Quebec, 3 from Ontario, 2 from BC, 1 from Alberta, 1 from Saskatchewan, 2 from Nova Scotia, and 2 from the US. So I did a literature review of the publications that were produced within these grants as declared in the PI surveys that the PIs have to fill annually. So in total, there were 47 publications that have been declared, including almost 240 authors from 68 organizations in 17 countries. About half of these publications explicitly acknowledge CSA funding, whereas the other half are enabled by CSA, meaning that they were declared in the PI survey, but do not explicitly acknowledge CSA funding in the acknowledgements. This plot shows the number of publications per year. We see a steady increase up until 2020 and then a drop in 2021. Not sure if it's related to COVID, but if I get a feeling from the discussions we've had with different PIs, this may have had an impact. So I don't know if we will see an increase again next year. We've also compiled the number of publications per leading country based on the first author affiliation. So not a big surprise, Canada is leading with 31 articles, followed by the US and other countries. We've also analyzed the journals in which the articles were published. So 12 of them were published in atmospheric measurement techniques, some others in JGR, ACP, atmosphere, couple and GRL. So we've also separated the publications depending on the main AO objectives they are advancing. And according to this the main objective, we have compiled some scientific results. So the first main objective was to advance the understanding of physical and chemical processes of the atmosphere and Earth surface processes that affect atmospheric composition. And the articles that advance this category focus on different processes involving aerosols, clouds, dust, pollutant emissions, snow, thermodynamics, and water vapor. Some others focus more on the goal to calibrate and validate new data from space mission, and they mostly develop or improve retrieval algorithms and compare space-based data to ground-based instruments or to models to evaluate the errors and biases on the space-based data. Some other focus on the development or improvement of computational models. And those that really focus on the models usually involve development of a data assimilation component, either in a chemistry transport model, meteorological model, or even a snow water equivalent model. Another goal was to develop synergies using complementary data. So some publications focus on combining satellite data together to produce climatological data sets. And finally, a common objective to them all was to stimulate research aligned with national and international priorities. And basically all of these papers advance climate science in one way or another. And many of them contribute to international initiatives such as climate model intercomparisons. We've done again the alluvial plot showing all the publications between 2018 and 2021 and the objectives they advance on the right. So I think that with time we see an increase in the advancement of the physical and chemical processes, but other than that, it's yeah. So for each of these objectives, we did a word count on every article's abstract that fell into these categories. So the two biggest categories were the papers advancing the understanding of physical and chemical processes, and those calibrating and validating new data from space missions. And these word cloud show us what are the topics that come the most often. So here we have water, vapor, the stratosphere is a big deal, and aerosols and radiative processes. Whereas in the calibration, well, we really see a focus on bias and quality of the measurements. We also compiled the scientific discoveries for these couple last year. So there was basically three papers published in GRL. One that tracks NO2 plumes over the Canadian oil sands. Another one that studies the super greenhouse effect and how it's transition between different convective regimes. And another one that studies the snowfall over the Arctic using CloudSat data. We've also compiled all the instruments that were used in these papers. So all of these instruments are used to advance the objectives. And there's 30 of them on 21 satellites, including three Canadian instruments. There are some more that we expect to see here, but we expect that when the last year of the grant is completed, some other publications will come out, and we will see even more of our Canadian assets here. Again, we've plotted the data user institutions across the world. As usual, we have most users in Canada and the US and Europe, and a couple in Asia. Here's a similar plot as I've shown earlier, showing data collaborations over time. We've added a description for the top 4 papers with the most authors. Again, it shows that there's an interest to using our data, and that it keeps going on over time. And finally, I think this is my last slide. Those are the models that are used for advancing the data analysis objectives. Again, separated in this time 5 different categories: chemical transport models, trajectory models, radiative transfer models, the GCMs, and the specialized models. And there's 21 models in total, 7 of which are Canadian. And I'd like to highlight, well, SASCTRAN that Doug mentioned earlier. There's also CAN-ESM5, that's a climate model used and developed at Environment Canada, that's used in CMIP6. And there's also GEMMAC, that's Environment Canada's air quality model. And yeah, I think that's it. I'm ready to take questions if there are any.
Okay, very cool. Thank you, Cassandra. That was a nice summary, some impressive work there. Questions for Cassandra?
Okay, I can go have dinner now.
Sure. Okay, I actually have one. I'm just wondering about how you categorize a scientific discovery. Is it basically just
we
published in
usually
GRL?
take the publications from Nature, Science, or GRL. And this time we only had the GRL.
Okay.
Yeah.
Can I ask a question here? This is Hind from L'Oreal.
Sure.
Yeah, so can you speak a bit about your outreach activities? You know, trying to, you know, reach out to as many new early career, mid-career people who are not directly involved with with Canadian Space Agency research. Just curious to know.
Yeah, I don't know much about it, to be honest. I started at CSA like 7 months ago, and I personally was not involved in any outreach activity. I think that the real public outreach activities are done by the communication departments. And so I cannot put my hands in there. But there's definitely some work to be done with academic side, and yeah, we need to provide more information about our funding opportunities and how to apply. And this is a discussion we've had.
I'm scared now.
So I think that these forums are a good way to, you know, try to reach a broader public. But yeah, this can be worked on.
Hi, this is Thomas. I'd just like to say that we did put out information about the announcements of opportunity on the website, or the list servers that we manage from CSA, as well as on the ARCU list server. So we did what we could to get the information out to as big a community as we could.
Good, thanks, Thomas. A comment from Jean Bergeron or a question?
Yeah, actually just follow up. I actually have a slide, my last slide, that may answer some of this, but we also have distribution lists that are a good tool to stay up to date regarding funding opportunities and such. But
Good.
I can go straight to my presentation if, unless there are other questions.
Yeah, okay, let's move to your presentation then, Jean. This is our last presentation of the day. Jean Bergeron from CSA, preparation for the SWOT mission.
Can you all see?
Yeah, looks good.
Is it in the right mode? Perfect. All right, so hi everyone. Sorry to be the only obstacle between now and supper for most of you, but someone's got to be the last. So Jean Bergeron, mission scientist at the Canadian Space Agency. And it's my pleasure to be among you today to provide a portrait of Canadian science and application activities in preparation for data from the Surface Water and Ocean Topography mission, also known as SWOT. But before I get too much into SWOT, first want to go back a little bit and provide a quick overview of what I like to call a family portrait of spaceborne radar altimeters. So I know many of you are atmospheric scientists. I'm going to pull the blanket over to the oceanography side a little bit here, but I'll try to make it understandable. So generally speaking, the way these altimeters work is they orbit the Earth and send a microwave pulse to the ocean surface, record the time it takes to return, providing a measurement of the surface elevation under the orbit track. Of course, signal processing is very complex, but that's the general idea. But these instruments have proven to be very useful tools for mapping the hills and valleys of the ocean surface. The SWOT comes after a long history of ocean altimetry, which enables us to collect valuable data and ensure continuity in the records of global ocean levels, which then enables us to study trends over time. As example, shown here on the right-hand side, which shows a clear and quantified rise in global sea levels, which is an important indicator of climate change. So the chart shown here on the left is 2 years old now, but still fairly accurate. There have been many precursors to the SWOT mission. And I'll just mention that this continued support for these missions requires considerable investments. So, for example, the combined cost for the 3 iterations of JSON satellites totals over $1.1 billion US, not adjusted for inflation. And the SWOT mission alone is in the same ballpark of $1.1 billion US. And this is because SWOT will use new technologies for the most part, which will grant enhanced capabilities compared with all of its predecessors. And so what are these enhanced capabilities? Or what even is the SWOT satellite mission about? So it's an international effort jointly led by NASA and the French space agency, CMOS, with contributions from CSA and UKSA, the United Kingdom Space Agency. So it's a science mission that will provide space-based measurements of water surface elevation over both inland water bodies and oceans. So it's going to have a near viewing altimeter, and we'll also be able to take angle measurements along 50 kilometer wide swath on both sides of the orbit track. All this using Ka band interferometric synthetic aperture radar technology. So each arm, there will be an antenna on both arms of the satellite that will emit orthogonal polarization beams that will allow the satellite to isolate each SWOT. So SWOT will not only continue to monitor the ocean levels, but it's also going to enable us to study ocean and coastal phenomena in 2 dimensions at scales that are currently not resolved by conventional imagery. So that's on the coastal side, but on the hydrology side, SWOT will also enable us to establish water budgets over lakes and rivers, provided that they're large enough to be observed, and even estimate the flow discharge from rivers, which could not be done before. So since 2015, CSA has contributed about $60 million for the procurement of key space hardware and for the advancement of science. The hardware consists of a critical component of SWOT, which are extended interaction klystrons, or EIKs, which are high power amplifiers for the microwave pulses that are transmitted by the main instrument, and the development of all EIKs, because there was an engineering model and 3 flight models, were all completed on time and under budget, which is a good news story for everyone. But I'm not going to stop here, because we've also invested in the science, along with Environment and Climate Change Canada and with Fisheries and Oceans Canada. So I think this speaks to the importance of the mission. So there, a busy slide, but there are 3 points I want to make from this slide. First is a number of data products will be developed from SWOT. I'm listing the main ones intended for oceanography here, but plenty more will be developed for inland hydrology. And I don't intend to go through each one individually. Maybe just a word about the first one at the top, which describes the data on sea surface height, sea surface anomaly, wind speed, significant wave height on the 2 by 2 kilometer grid. Point number 2 is that all of SWOT's data products will be hosted and distributed by one of NASA's data center, known as PODAC. And for those interested, you can already get familiar with some of these data sets right now and get used to the format and see sample products by visiting the PODAC website. And point number 3 is that all of these beautiful, gorgeous products will be, and I quote, available fully, openly, and without restriction. And this applies to Canadian users as well. Now, regarding upcoming milestones, the obvious one is Swot Launch. So we are considered to be in the last phase, or last stage, I should say, of phase D. The payload has been assembled and integrated with the spacecraft. The whole package currently resides in France for final testing, and then it will be shipped back to the US to be launched on a SpaceX Falcon 9 rocket from the Vandenberg Air Force Base in California. So SWOT is scheduled to be launched no earlier than November 2022. And for the moment, this is still coherent with backstage discussions for a launch in late 2022. So if everything keeps to schedule, launch should occur in late November. Engineering checkout will follow for about 3 months, and then CalVal will begin the following 3 months after that. So late February, early March, and end in late May, early June 2023. So during that time, the satellite will follow a fast sampling orbit, collecting data with a daily return period over limited area. But after this phase, the satellite will be pushed to a different orbit for nominal operations and cover 90% of the Earth on a 21-day return period. So on CSA's end, we put in place a contract to ensure their support for the EIKs during the final stages of testing and during SWOT operations. So the necessary pieces are in place for us. So far, so good. Now, on the science scene, there are many linkages both within Canada and internationally. So CSA supports these activities in various ways. we have had memoranda of understanding, or MOUs, with HFOC and DFO. We participate in the development of SWOT science, and these MOUs have been developed, not developed, but supported by 3 grants to Canadian universities, Université de Sherbrooke, University of Toronto, and McGill University. And we have also set up our own Canadian working groups to facilitate both planning activities, sharing knowledge, that sort of thing, particularly since the more recent award of grants to Canadian universities under CSA's Earth System Science Data Analysis Program, which Cassandra just presented on. So the aim here is to make use of SWOT data outside of the baseline science requirements of the mission. So we have a total of 4 grants for SWOT awarded in spring 2021. And I was inspired here by Cassandra's numerous alluvial plots in her presentation, so I decided to give it a try for the slide. I'm not sure how it turned out, or if it turned out to be as neat as I was hoping for, but at least it tried. And also just mentioned that we have an implementing arrangement with NASA, and a number of Canadians actively participate in the SWOT science team as well. We collaborate with international researchers funded through the NASA and CNES joint call for the 2020 to 2024 SWOT science team. All right, this support from CSA ensures that Canadian scientists have been and will continue to instrument key sites in Canada under the SWOT Calval orbit, including multiple lakes and rivers, as well as the Atlantic and Pacific coastal regions. And so our scientists are closely involved in SWOT Calval activities. So what I'm showing here is an attempt to map out Calval sites over Canada. So there are sites that meet certain standards in terms of instrumentation and are officially recognized as Tier 1 or Tier 2 sites by the SWOT team, but there are many other sites that are being studied and instrumented. And we're trying to show these in blue on the map. So Canadian scientists are enhancing their numerical model capabilities for these sites especially. Of course, training highly qualified personnel along the way and ensuring that the quality of SWOT products will live up to their expectations. But of course, there are unexplored opportunities where SWOT could potentially shine, for example, regarding snow cover properties. So if that interests you, let me know. More info on that point in a minute. But first, I want to mention that there are also activities being pursued involving the RadarSat constellation mission, which could be used to enhance SWOT products or generate more knowledge than what either mission alone can generate. So there are a number of areas identified by the Canadian SWOT science team, and they're working toward this. So you can see a non-exhaustive list here. For example, in order to extract water volume estimation, one needs not only water elevation, but also information on the lake geometry. So particularly near shore topobathymetry. So SWOT will provide these elevation and water extent maps, but that needs to be validated, and also more passes with finer resolution is always useful. So there are ongoing discussions with our scientists and with the French team at CNES to make that happen both inside and outside Canada. So that would be particularly timely for CNES, especially since the unavailability of Sentinel-1B, on which they were partially relying on for Calval. So this is ongoing, more to come soon. So just a last slide here. All in all, point here is that this is a good news story. We are making SWOT happen. SWOT data will be freely available, and there are opportunities not yet explored, but we are moving to ensure that the data gets used to the benefit of Canadians. So should there be an interest in pursuing activities to broaden the spectrum of science and applications for SWOT, you're welcome to submit a proposal at the next call for Earth System Science data analysis. And on this point, so CSA funds many other projects, and Canadians are also eligible to participate in many programs hosted by international agencies like the European Space Agency. And the easiest course of action, I believe, to remain updated on new initiatives or funding opportunities is to subscribe to our mailing lists. We have, well, I think fairly self-explanatory channels here, posted to the atmospheric sciences, or surface sciences, and the solar terrestrial sciences. So just send an email to any or all of these lists, depending on your research interests, and just respond to the email for confirmation that you'll receive, and that's it. So I thank you all for your time.
Great, thanks, Jean. Thomas, looks like you have a comment or question.
Yeah, Jean, could you go back to slide 4? Yeah, so I see that there are some other data products, like the third one from the bottom about radiometer measurements of wet troposphere content. I just wonder if you've heard in the science team meetings for SWOT of atmospheric science people using these data. I know their main purpose is for correction of the interferometric SAR, but are they useful, or do they have qualities different from other radiometers that are flying?
That's an excellent question, Thomas, and very timely as well, because we have our next SWOT Science team meeting at the end of this month. And I understand that one person's trash is another person's treasure, right? So while the Earth surface community is trying to get rid of or make corrections for the atmosphere, atmosphere scientists can use this to their benefit. To be honest, there has not been, to my knowledge, any talk, any discussions regarding, transfer of atmospheric data or any atmospheric science talks at these SWOT Science meetings. But this is a point that I can bring up in a couple of weeks.
Thank you.
Thanks. Comment from Hind, question?
Yes, thank you for your presentation. The question I have is regarding, a very general one, but is in case you have come across ideas that were submitted to the CSA for the effect of dust deposition on oceans and how that deposition process affects the ocean productivity, because it has consequences on CO2 uptake.
The question is if we have received proposals?
Proposals or talks about the capabilities of the satellites you're talking about to actually look into dust deposition and how it affects ocean productivity. Is that something the satellites can do?
I would say, well, so SWOT will measure water surface elevation, mostly. So unless it affects the water levels, it's unlikely that it's going to see other things.
Okay.
But who am I to, I have not looked at this myself.
Yeah, because I've seen satellite images of chlorophyll distribution in oceans, and chlorophyll has different optical properties than the surface ocean, and this is how they actually quantify ocean productivity in different parts of the world. So I wasn't sure what type of satellites they use of that, but since you mentioned your work is related to oceans and atmospheric processes, I thought to ask that question to see, if you have thoughts on this.
That's a fair question, and maybe I'll use this opportunity to plug in another pre-project initiative, which we refer to as Watersat, which proposes to take hyperspectral measurements over the ocean and over inland lakes as well, which would grant which would yield an indicator of water quality, including algal bloom and things like that, which would probably be more relevant to atmospheric dust deposition on the ocean. But for SWOT, it's really looking at water levels.
Okay, great. Thank you so much.
No problem.
Okay, let's take one last question from Goki.
Oh, hi, Sean. For excellent talk. So maybe I don't have any question. I think I would just like to thank you for to provide a great introduction of this SWOT mission. So, I'm the DF4 scientist who is leading on the ocean part for SWOT program and have been collaborating with CSA, especially the Jean and the Thomas. So I just want to make a comment, to the question actually raised. I would say, yeah. So one of the most important contribution from SWOT probably is actually to understand this kind of vertical exchange in the ocean. So because the conventional satellite altimetry, as Jean introduced, can only resolve in ocean, large scale ocean circulation, like large eddies and large currents. And so that's important, to horizontal transportation. But the SWOT will be able to resolve very small scale ocean circulation. So the target is we call the sub-mesoscale. So we are talking about maybe 10 kilometer or 5 kilometer. So that part is very important for the vertical transmission of the water properties. And so can very well resolve a coastal fronts and there's small scale features and how, there's pollutants and carbon dioxide or atmospheric pollutant, how they can transmit in the ocean vertically. So I think it's very relevant to the question raised in the yes. SWOT will be very useful actually in addressing this kind of scientific issues and for societal applications.
Good. Okay, thanks for the comment. So Kaylee, if you're still awake, maybe we'll end it here.
Yep, I think we declare it done. Thank you everyone for your participation, sticking it out till the end. I think we had a great session.
Yeah, it was a good day. Thanks everyone.